Hello everyone, this is Yongqi Shi from University of Basel. Yeah, it's my honor to share our work towards a frequency-tunable microwave magnetic field imager with ultrathin atomic vapor cells. So our work is supported by the project Maximo, and I also would like to thank our collaborators in CSEM, which is the Swiss Center for Electronics and Microtechnology, and also the group Gaetano Miladi from University of Neuchâtel. So in this talk, I'm going to share you three contents. The first one is our motivation to do this gigahertz or terahertz field imaging. So I will compare, let's say, the conventional techniques to image the gigahertz field with some newly emerged atomic vapor cell methods. And the second part, I will show you our some measurements, some images on a fixed frequency microwave imaging, a microwave magnetic field imaging. And the third part, I will show you some latest results towards a frequency-tunable microwave magnetic field imaging. So for the first one, as we all know, microwave is, let's say, everywhere around us. So it's also very essential, ranging from fundamental quantum science to some important industrial sectors. For example, people use the microwave above an atomic chip to manipulate ultra-cold atoms. People use microwave coplanar waveguide to produce this superconducting quantum qubit. And in clock community, they use microwave to drive the clock transitions. And yeah, it's also very important in communication industry, in medical imaging, and also security check. And talking about some conventional methods, so initially people use bulky antenna as a receive antenna to measure the local local electric field at some fixed microwave frequency. And afterwards, people developed a whole system of microwave imager with a scanning magnetic field probe or electric field probe. These are very tiny metal probes. And afterwards, there are some other contactless methods that are appearing, like electro-optic imaging, electron beam method, and electro force microscopy. All of these conventional methods, they have drawbacks of they have to pre-calibration. They have to pre-calibrate it, and especially for this metal probe, they will probe the fields from the device on the test, and you have to scan point by point, so it's not a real imaging. Okay, so then we think about our friends atomic vapor, so dielectric atomic vapor cells. So there are some work appearing recently. So people use Rabi oscillations of rubidium atoms to image the near field magnetic field at 6.8 gigahertz, and also use the EIT splitting from the Rydberg atoms in a cell to image the electric field distribution, and also use this terahertz to optical conversion to image a field that is at even, like, let's say, half terahertz frequency. So the advantage of atomic vapors are they are intrinsically calibrated because the measurement of the amplitude, they are directly linked to some well-known constants, and you will reduce the field perturbation, and there are less crosstalks, and the spatial resolution can be reduced below 100 micron, and you can do parallel imaging. Okay, for the second part of my talk, I will draw your attention to our former work on a fixed frequency microwave magnetic field imaging. So in that work, we were using a ultrathin atomic vapor cell here, and which is connected to a vacuum system by which we can change the buffer gas type and pressure into the vapor cell. And it's an ultrathin one, and we designed a coplanar waveguide chip. Yeah, these are some parameters of our system and cell that we were using. And talking about the principle, so different from a typical, let's say, optically pumped magnetometer, here we were using hyperfine pumping, meaning that we first shine a pump laser pulse to pump the atoms in F equals to 1 hyperfine manifolds into F equals to 2 to F equals to 1 hyperfine manifolds. And then we shine microwave pulse to induce some Rabi oscillation to move some atoms from f equals to 1 back into f equals to 2. And then we shine a second probe beam to detect, let's say, how many atoms are left on f equals to 2 state. So by scanning the duration of microwave pulses, we can get such a nice Rabi oscillations, and whose amplitude is proportional to the populations on f equals to 2 manifold, and whose frequency is proportional to the local microwave magnetic field amplitude. So we use a CCD camera and we do it parallelly. So we feed the Rabi oscillation frequency in a spatial resolved way, then we can get information. We can get an image of a near field magnetic field at 6.8 gigahertz. So let me show you a nice movie. We call it a Rabi oscillation movie. As you can see, this dt is the duration of microwave pulse. With increasing of microwave pulse, you can see atoms in different regions, they are performing Rabi oscillations in different frequencies, meaning that the larger the microwave field it is, the faster the Rabi oscillation will, let's say, oscillate. And with this different Rabi oscillation frequencies, we can extract the local microwave field. Yeah. Yeah, and yeah, here's some images. Let's say by changing the direction of a static magnetic field, we can image the three components of our near field microwave magnetic field above this zigzag chip. Yeah. So to be noticed here is the field is not very large, around 100 microtesla. Okay, so far all the images that we took are at a fixed 6.8 gigahertz frequency. Yeah, but if we want to increase our technology readiness level to increase some other frequency, we have to make our technique frequency tunable. Now here comes a new setup. So in this new setup, we designed a pair of permanent magnets, which is comprised from samarium cobalt, and it has the advantage to offer a tunable range from 0.2 Tesla to 0.55 Tesla, and it can offer a rather homogeneous region. And these two materials, samarium cobalt, they have low temperature drift among all the other, yeah, let's say permanent magnets materials. And we also use a setup testing cell here, which has a rather thick thickness, 2 millimeters. And we first build a model of optical absorption in different buffer gases, and we measure this optical absorption spectroscopy we put the cell in center of the magnets, and in this low probe limit, we found a very good matching between the theory and experiments. Okay, then to understand, let's say what is the frequency range that we can tune, we did some theory calculations. This is a microwave frequency as a function of P0 field, and this is a microwave transition strengths as a function of static magnetic field. So from our current setup, we will be able to image for microwave frequency in the range of 3 gigahertz to 21 gigahertz. Okay, so to further investigate the homogeneity of the space that we will put the cell in the permanent magnets, we, let's say, used a new scheme. We use a pulsed double resonance imaging scheme in which we fix the duration of microwave field, but we scan the microwave frequency, and we took pictures like this, and different pixels will show different double resonance peak, and this detuning of the peak will be proportional to the local static magnetic field. So with this way, we can get information of the homogeneity of the static magnetic field. So as you could see, the whole region of the cell, let's say this 5 millimeter times 5 millimeter, the inhomogeneity is less than 0.3%. So it is already very good. And then we use a test antenna to drive our famous Rabi oscillations. This is our latest result. As you can see, in the most homogeneous region in the center, we have P1 pixel and P2 pixel. They are driving different Rabi oscillations at 15.1 gigahertz. I mean, this is a random microwave frequency. So which prove that we can image the, let's say, microwave amplitude at 15.1 gigahertz in this most homogeneous region. Yeah, another point with this with counter cell is it has rather thick thickness, 2 millimeter. So to overcome this problem, in collaboration with our partners in CSEM, we designed several new types of MEMS ultrathin atomic vapor cells. It has pure rubidium-87 and with 0.2 millimeter of cell thickness and with 0.2 millimeter of sidewall thickness. We have different dimensions, and we measure the buffer gas pressure precisely by measuring the optical shift and broadening together. And this is a photo we took in the laser scanning a microscope to measure the flatness and also the homogeneity of the thickness. Yeah, you can imagine this is rather a large cell with a very thin thickness. And the last result will be our latest result. Yeah, with this new cell, we performed a pulse double resonance measurement. As you can see here, we can measure, let's say, a more larger area of homogeneity of the static magnetic field with a new cell. Yeah, so which means that the new cell, this ultrathin vapor cell, is not a nightmare. We can still work with it. And in this left picture, I show our antenna, which is also a home antenna. And this is the cell that we are now using. So to summarize my talk, I discussed our motivation to do this gigahertz or terahertz field imaging with atomic vapor cells. And I show some results of fixed frequency magnetic fields at 6.8 gigahertz. And I show some latest results of our behaviors on frequency-tunable microwave imaging. And we are also considering, let's say, further homogenizing the magnetic field, this large static magnetic field, and to use some alternative sequences or methods to measure unresonant Rabi oscillations. And for rather long plane, maybe we could develop some integrated microwave detector or imager, let's say, based on atomic vapors to make it to be a very integrated package. Or we are also looking for some potential industry and medical applications. Okay, this is a picture of a family portrait of our whole group. Most of my colleagues, they are working in cold atoms region. And I will also thank Roberto Mottola, who assembled the magnets and oven, and my former colleague Andrew Horsley, who is now in Australia. And we also have a atomic vapor team, Gianni Buse, Roberto Mottola, and Yannick Wolters, who are working on atomic vapor-based quantum memory. Okay, thank you.
Super nice talk. Thanks a lot, Yongqi. It's actually quite cool to see this project develop because I think the original publication was from 2017, so it's nice to see that you're keeping it and improving it and developing it. Are there questions? Oh yeah, that's a question by Gianvito Lucibedo. Do you want to read the questions or should I ask?
Yeah, I just got this question. In space science or satellites, well,
maybe repeat the question. So for
the question is, am I aware about the applications of microwave atomic sensors in space science or satellites? Yeah, I have to admit I'm not aware about some space science with, let's say, microwave atomic sensors. Maybe no, but I'm aware that there are some groups in US. They are developing some microwave detectors based on Rydberg atoms to detect very tiny, let's say, microwave signals. Yeah, but I'm not sure whether it can be used in space science. That would be my answer.
Thank you. Maybe while I think you spent quite some time in your talk about it, but I mean, how does it compare to antennas? I mean, like especially in sensitivity. I mean, I know that you like beat normal antennas in spatial resolutions, but I also have no feeling on how much more sensitive just a piece of wire is with respect to your atoms.
Yeah, okay. This is a very good question regarding the sensitivity. So the former work performed by Andrew Horsley, the sensitivity was on the level of micro Tesla per root hertz, and it is not very good. There are two reasons. The first reason is because you see it's an imaging process, which means if we want to image, for example, 100 times 100 pixel image, so it's really difficult to. It's like 100 magnetometers working simultaneously. So the sensitivity you could imagine it cannot be increased to very high level. And this is one point. And based on this, in our new setup, we used a faster camera to decrease measurement time. And in this newly measurement, the sensitivity I can reach is in the range of nanotesla, so 20 nanotesla around per root hertz.
Cool, thank you. There's another question in the chat by Peter Schwind.
Yes. So our goal is to get a homogeneous region between this pair of permanent magnets. So by lifting the distance of upper and bottom part of this magnets, we can change the range. So that's why it's a limited field. Can I achieve your whole?
There's maybe one last question by Igor Zavukov. What about sensitivity of the method based on heating with the camera? What does he mean?
You mean heat the cell with the...
Igor,
didn't get the question.
Igor, could you elaborate?
Microheater heats material.
Well, yeah.
Maybe I can talk.
Yeah, go ahead.
Yeah, I'm just if you have seen film or something and you apply microwave somehow, heats it, and then you could see maybe temperature changes.
Yes. Oh, now I get it. Yeah. Yeah, this is a very good question. So typically at such high frequency, I mean 15 gigahertz, if you just keep the microwave on, then for sure the temperature of the cell will just increase immediately. While in our case, we use a pulse regime. So the real, let's say the real time of microwave is on is just, let's say, microseconds. So the heating effect, I have carefully calibrated it. It can be negligible. But in the continuous double resonance method, it cannot be neglected. So I keep the microwave on and wait until there's a, let's say, equilibrium state. So I remeasure the temperature considering the heating from the microwave.
Still, I think interpretation a little bit different in my question. So you interpret it as a result heating on your system. I'm saying just using some, let's say water would be heated by a microwave, and you could see the temperature with some infrared camera or something. I don't know, just to have some other alternative.
Yeah, there are some infrared cameras to measure the heating effect. Yeah, but not sure how, let's say, what is the spatial resolution of it, or big, but it is a power measurement. Here we are performing, let's say, the field amplitude measurement of a microwave. Yeah.
Okay. Thank
Good.
you.
We can also discuss this maybe after the workshop. But now let's thank Yongqi again for his nice talk.
Yeah.